Hello, I'm Clint Panion. This will be the second fluids video I'll be doing, so let's just dive right into it. Water is pumped from the water tank shown in diagram A below. The entrance to the pipe section is sharp-edged. That's important. The pipe is cast iron and the total length is 2 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and actual head rise is provided in the pump specifications and is shown in diagram B. So part A, determine the volumetric flow rate for the system. Okay, so starting with this problem, we're going to use the Bernoulli's equation that includes head rise and head loss to cover every base. So that's just P1, pressure of 0.1 over specific volume of the fluid, plus the kinetic energy at state 1 over 2g, making sure this formula is correct, plus the height at 0.1. Oh, wait. Let me add in the head rise of the pump. This is, yeah, it's called head rise. It's equal to P2, specific weights, plus the kinetic energy, all in state 2. It's supposed to be a 2 times gravity. And the head loss associated with the pump. Okay, so we're going to be looking at our system now. We're going to put 0.1 here, 0.2 here at the exit. Okay, so to cancel a few things out, at 0.1, it's exposed to the atmosphere, so P1 cancels out. P2 is also exposed to the atmosphere, cancels out. At V1, it's at resting fluid, so there's not going to be any kinetic energy associated with that. No velocity at 0.1. And at 0.2, you're going to have this fluid that's gushing out still, so there will be some kinetic energy associated at 0.2, so that stays. And you have your head gain from the pipe and your head loss from the pipe. So this equation is now going to cancel out into the Z1. Oh, wait, one more thing. Z2 will be our ground, so Z2 also cancels. So Z1 plus head rise of the pump is equal to the kinetic energy component plus the head loss component. All right, here's the idea with head loss. Head loss is going to be the loss in pressure associated with two things: the friction of the water flowing against the material of your pump, and that's going to be major head loss. And the minor head loss is going to be the sharp edges, and that's generally associated with the nooks and like bends of your pipe and certain components like valves or T's that may also be in your system. But in our example, it's just a sharp edge. So that's all we will be addressing. Let's write out our formula for minor head loss. So that's going to be KL, or your loss coefficient, times V2 square over 2G. The reason these minor and major head losses are only referencing V2 is because they all occur in this stretch of pipe here where section 2 is. Section 1 is just the giant large tank, so there won't be losses occurring with V1 or anything like that. Okay, so this is kind of you always have a varying loss coefficient depending on your bend. We're given sharp edges. This one's kind of tucked away. Like I tried looking at the textbook and looked for it. I don't see anything about sharp edges here. It's actually tucked away in one of the figures throughout chapter that covered this topic. I've written down it's page 435, figure 8.22. But for a sharp edge, your loss coefficient would be 0.5. Okay, so now for the major head loss, you're going to have a friction factor from the friction of the water against the material of your pipe times the length over the diameter of your pipe times V2 square over G. 2G, excuse me. That's the kinetic energy component. All right, so this is, we are told in the problem that the pipe is observed to be fully turbulent. So that means we gotta look at our Moody diagrams to solve for our friction factor. I've printed one out over here. Let's look at it. All right, so let me adjust my camera a little. So we can't solve for Reynolds number because we don't have velocity yet. But we are told that it is completely turbulent. So we're basically going to be looking in this giant region here where all the flows just kind of flatten out. Turbulent, your flow just kind of like flattens out. It doesn't have this gradual decrease anymore. It's just flat. So we're going to look at the right side here. This relative roughness value is made of epsilon over d. To get the epsilon, that's going to be your roughness coefficient. It's from here. What was our material? Going back to the problem, it was cast iron. Okay, so that's here. We're going to be using this one, the millimeters version. We're going to calculate relative roughness. It's going to be equal to epsilon over d. It's going to be equal to the epsilon here. Make sure this is in meters to be so the units cancel out with your diameter from the problem. What was the diameter? It was 0.07 meters. And that should get you 0.00371. All right, so now we're going to look at the Moody diagram on the right side. This is 0.02, 0.004, 0.0038. It's going to be somewhere a little under this. Take your straight edge. I have a really long straight edge. I'm going to do this in blue pen so it's clear to see. All right, it's going to be about partially through 0.025, 0.003. So because it's closer, I see it as close to 0.003, so our friction factor is going to be 0.028. That's all for the Moody diagram. And friction factor would be 0.028 for the major head loss. All right, so now we can start plugging everything into the formula a little bit. So Z1 plus the head rise of the pump is going to be equal to our kinetic component, kinetic energy component, plus there will be minor head loss, so you have to include that, 0.5 times V2 square over 2G, plus the major head loss component, 0.028 times length over D times the V2 square over 2G. Well, we have a problem in our current equations that we have only one equation but two unknowns, this head rise and the V2. We're trying to solve for V2 in order to get the volumetric flow rate correct. So this is where our equation from figure B is going to come into play. If Q is equal to VA, the volumetric flow rate, then head of pump has this Q square in here. So Q square will be the VA square. We could solve for area, so that will just be pi over 4. That'll include everything else in head rise. 20 minus 2,000 pi over 4. Your diameter Pi over 4d squared is the area. Then you have V2. That's going to be squared. The head rise formula we'll be plugging into our Bernoulli equation will be, let me write it out. It will be about 20 minus 0.0296 V2 squared. All right, and this will be a little weird, but the units associated with here are all going to be meters, even though we did the area calculation. All right, so plug everything in now. We're going to isolate the V2 squared over 2g as a common variable for all of these loss coefficients. And so let's just plug everything in. Z1 will be equal to, not quite, Z1 plus the 20 minus 0.0296 V2 squared is equal to V2 squared over the 2g, 0.5 plus 0.028 times length over d. So that's going to be the length of 2 meters over diameter. Plus the 1 from the kinetic energy. Okay. Now, I'm just going to plug in Z1 now. It's going to be the 6 meters from the diagram. As I'm doing it, I'm going to plug in the gravity. Okay, so from this, you should get 26 is equal to, let me do this real quick. 1 over 2 times 9.8, 0.5 plus 0.028. 2 over 0.07 plus 1. You should get your V2 squared is equal to adding this over to the other side, plus all this is going to be equal to 0.11735. Okay, so if you're confused on how the units worked out, the solid numbers with no V2 attached to it, these units are going to be meters. On this side, the units for this are going to be the inverse of gravity's units. It's going to be seconds squared per meter because the gravity was in the denominator. And when you divide everything out, your V2 will be square root of the 26 meters over the 0.14695. And that was the second square per meter. So you get meters square per second square in your square roots. That's good. So now you have a velocity units, and so your final velocity should be 13.3 meters per second. And now that we have the velocity at 0.2, we can solve for flow rate. It's a long time coming, but we're almost there. Q is equal to VA. It's equal to the velocity we just found times the diameter, the area of the pipe again. Pi over 4d squared And that will get you a flow rate of 0.0512 meters cubed per second. Okay, that was all part A. That's the real meat of this problem. We're going to finish part B in no time. So, show the observation that fully turbulent flow was correct. All we're going to do is solve for Reynolds number. And for Reynolds numbers above 2000, you're good. That's going to be fully turbulent. But when there's numbers below 2000, that's considered laminar flow. So to prove that the flow is actually turbulent, if we get it higher than 2000, then we're in the clear. So velocity times diameter. Velocity comes from here. It's just 13.3 again. Times your diameter of 0.07 meters. All over the kinematic viscosity. It doesn't specify temperature. I'm just going to use the standard for water, which is 1.12 e to the negative 6. It's going to be meters squared per second. All right, so our Reynolds number is going to be 831,250. And as we said before, since our Reynolds number is greater than 2000, we are fully turbulent. Yes. All right, so part C. If the pump is 70% efficient, determine how much power must be supplied to the pump. Okay, so efficiency is this symbol of 70% or 0.70. We do have an equation for efficiency of a pump. That's just going to be this Pf value over your work dot value, the rate of work in your shaft. All right, so this idea behind efficiency is conceptually, you're seeing how much of the work you get out from the work versus the work you get in. So this is going to be power supplied. And this will be power gained. And we're going to be solving for the power supplied relative to the efficiency they provided us in the question. The equations for Pf and work dot are almost identical, but we're just going to say, for the sake of putting it as an equation, the power gain will be equal to efficiency or work. Oh, excuse me. Work dot, the shaft, over efficiency. So work dot or power, so power gained is equal to rho GQ, specific wave of fluid, times volumetric flow rate times head rise of the pump. We're going to use the head rise of the pump from figure B equation, so we don't have to solve for this again. And we're just going to use the rho G and the volumetric flow rate we found in part A. And we're going to divide it by the efficiency as seen here. So let's do just that. 999 kilograms per meters cubed is the density of water. G, 9.8 meters per second square. Volumetric flow rate, 0.0512 units are meters cubed per second. Head rise, this is a little weird because head rise includes a Q square, but the units are just going to be meters, guys. It's just a relationship between Q and head rise. So plug everything in. I'm running out of room because this equation is just so wide. 0.0, it's just this Q value here. This value is supposed to be square. Remember, the units will be meters for head rise. So, oh yeah, over the efficiency value of 0.70. So power supply needed to supply the pump will be equal to, let me type it out real quick just to make sure. Plug in the right numbers. You should get around 105, 10,567.3. Now the units, let's work that out. These meters cubes are going to cancel. Kilogram meters will stay. You're going to have a, let's do this over here. You're going to have kilograms meters square per seconds cubed. And that is equal to a Newton meter per second, which is equal to a joule per second, which is equal to a watt. So this is in watts. So if we divide by 1,000, we convert to kilowatts. Do 1 kilowatt over 1,000 watts. So power supply is going to be equal to 10,567.3 watts, or just 10.6 kilowatts. And that is the power, so that's how much power needs to be supplied to the pump. All right, that's the whole problem. Thank you for watching. It was lengthy, but I think it was worth it for our understanding of how all the units and numbers cancel out. Thank you for watching.